So we are covering Fourier series.
Do I just Google EC2 or UT?
So this is actually a very important theory due to Joseph Fourier. And he established this around 1800, just slightly after the French Revolution. Okay, do you remember when the French Revolution was? Okay, he fought for the French Revolution, won with Napoleon to Egypt, and he studied canon, and he discovered this Fourier series. And he said that any function of time that is periodic can be expanded in terms of a summation of sinusoidal signal, okay, signals that are time harmonic. If you look at this signal, usually we call it a time harmonic signal, because this signal just, the real and imaginary part just go like that, like a sinusoidal signal. Okay, this is called a time harmonic signal. Okay, so it's harder to draw a complex number, but I can draw its real and its imaginary part and show that it's just an oscillatory signal with an imaginary and the real part. Okay, and that you can find its coefficient by using this method, that f sub n is given by this formula over here. Integrate the function f of t e to the minus j n omega naught t dt. Okay, where f of t is periodic, which means that f of t minus an integer, let me use another term for an integer, maybe k times a period is equal to f of t. This indicates that this is a periodic signal. Okay? So if the f of t is periodic, you can integrate over one period, that's what this means, and multiply by e to the minus j n omega naught t, and find this Fourier coefficients quite easily. Okay? And how do we know that this Fourier coefficients exist? Converges, okay, that's a good point. You better make sure that when you perform this integration, this is not an infinite number. If you perform this integration and you get an infinite number here, when you substitute back into this series, you get an infinite number here. So that's not good. So the reason for existence of this series implies that f sub n is finite. Okay, in order to guarantee that f sub n is finite, you want f sub n to be equal to 1 over t f of t e to the minus j and omega naught t. Okay, and you know how to find magnitude of a number. And in general, every term of this series or this expression is going to be a finite number. And let me make the thinking a little bit easier for you, and think of this as a finite summation of maybe j equal to 1 to capital N, f of j delta t. There should be a dt somewhere. Okay, e to the minus j n omega naught j delta t delta t. I can think of an integration as a case where I break this integral summation into tiny parts and then letting the tiny part go to 0. And in the limit, when the tiny part becomes very small, I will get the integration back. This is calculus, right? where I have actually just let t be equal to j delta t in the above summation. So every term in this summation is a complex number. Okay, so this is like magnitude of sum of a complex number I or j equals to 1 to n. Okay, and when the sum complex numbers up, you know that on the complex plane, if I have the real and imaginary part, C1 might be a number like this, here C2 might be a number like that there. So if I sum complex numbers like summing vectors on the complex plane, right? C1, C2, C3, C4, C5, and so on. Okay? And if I sum over after many things, I might end up with the n number, Cn over here. And this is the end product of a summation. Okay, this would be the sum over Cj, j equals to 1 to n. Okay? When the sum complex numbers are this, how it occurs. And one thing is obvious. One thing is obvious is that the magnitude of this sum, which is the length of this line, must be less than or equal to the magnitude of individual numbers. Can you see that this equality or inequality has to be true? Right? It has to be true because if you were to sum the complex number up, get a total complex number, find its magnitude, that line must be less than the sum of the individual magnitude of the complex numbers. Okay, this is quite true. Which means that if I were to sum these complex numbers up, it is going to be smaller than the sum of the individual numbers. So this must be less than, okay, this number over here. And then I take the magnitude of these individual numbers over here. I will just get magnitude of this number times this number, but what is the magnitude of this other number? I'm sorry to use j. J is not a good number to use because j is getting confused here. So maybe I should change it to p. Excuse me. Change it to p. Change it to p. Very soon I'm going to run out of things for integers. Okay, p. And if I were to take the magnitude of that number over there, what would I get for the magnitude of the second factor? It's 1, right? I will just only get the magnitude of this. So I will have just this left. And delta t is always a real number. This must be true. Okay, that inequality must be true from this picture over here. But this is just equal to, as a limit when delta t goes to 0, okay, this is just equal to an integral again, dt. Okay, that is equal to that. Okay, and if this integral always exists, it always guarantees that f sub n will be finite. Okay, if this is less than infinity, it implies that f sub n is finite and exists. Okay, can you see that? So the existence of a Fourier series is that you have to have this number converging, and this is called absolute integrability. So if a function f of t is absolutely integrable, then the Fourier coefficient exists. Because you find the Fourier coefficient by this method over here. Are there any questions so far? Okay, can you see the reasoning logic here? Okay, let me repeat. Having this Fourier series expansion, you find the coefficient with this formula. Okay, in order for the Fourier coefficient to exist, the right-hand side cannot be infinite. So let's look at the right-hand side and see when it can be finite in number. So we take the magnitude of this equation we get the right-hand side. So we take the magnitude of the right-hand side, but it's easy to think of the right-hand side as a summation of complex numbers. Okay? If it's a summation of complex number, this bound, this upper bound must be true. Okay? So if you think of the right-hand side summations of complex number, it must be bounded by this number over here. This number again can be written as an integral. Okay? So this integral must be a bound to this number. So if this integral is finite, it implies that f sub n is finite, and then Fourier coefficient exists. Okay? Is this clear? Yes?
Where does the e to the j and omega p delta t go?
Oh, when you take the magnitude of a function multiplied by a theta, okay, it's the magnitude of the function itself times the magnitude of, I think this is a rule of magnitude. Then the magnitude of the second term is 1, it disappears. Okay, leaving only behind the magnitude of this. So this will be just the magnitude of f of t. Okay, because that goes. Any other questions? Okay, if no question, then let's figure out how we can get a formula such as this one over here. And where does this formula come from? Okay, let's figure that out. Where does this formula come from? I talked about vectors last time. But then it dawned upon me that many of you may not know what a vector is, right? So I told you about vectors, n vectors, 3 vectors, but many of you might not know what a vector is. But I presume you have learned about vectors in some other courses, right? So let me revise the concept of vectors again. Say, if we have a 3-dimensional coordinate system, and if we have a vector pointing in 3 dimensions, this vector may be called vector A, then this vector would have 3 components. And to find the 3 components, I project them onto the z-axis. Okay, the z-axis projection will look something like this. And let me call this value AZ. And then this is the x-axis projection. Let me call this value AX. And this is the y-axis projection. So vector A can be written in many ways. One way to write the vector A is just to represent it with 3 numbers. Okay, some courses would write it as something like this. And some courses might write it as XAX plus YAY plus ZAZ. And some courses will write it as A1 maybe bar AX plus A2 bar AY plus A3 bar AZ. So depending on which course you learn, vectors are written differently. Okay? But I prefer this method of writing a vector. That represents a vector with 3 components, x, y, and z. But finding the Fourier series coefficient is very similar to the concept of vectors. Okay, let's see where the similarity is. So if I have a 3-vector A consisting of 3 components, I can write it as the sum of 3 unit vectors, 1, 0, 0. This is a vector that points in what direction? X direction, right? And then this is a vector that points in. Very good, you know what the vector is. And then AZ, 0, 0, 1. So this is like the vector that points in the x direction. In some courses, you would have called this x hat. This would be y hat. This is z hat. And some courses might call this A1, A2, A3. And some courses might call this I, J, K. Okay? Different courses give you different notations. For this unit vectors pointing in 3 different directions. So I can often write any vector as the sum of 3 unit vectors. I call this U1, U2, U3 plus AY U2 plus AZ U3. And what do you notice about these unit vectors? They are also peculiar in the sense that they are orthogonal. If I were to write U1 transpose dot U2, and I'll have to tell you what this U1 transpose is. It just dawned upon me that some of you might not know what this notation is. Okay, if you take a transpose of a vector, if U1 is something that looks like this, U1 transpose is something that lies on this side. Okay, it's 1, 0, 0. Okay, something that lies on the side, and if you do this product, which is inner product, okay, U2, it will be something like 1, 0, 0 multiplied by U2 might be 0, 1, 0, something like that. And then when you multiply them together, you multiply this number, you multiply this number with that number, you multiply that number with that number, and you sum them up. And what do you get in this case? 0, right? It's 0. And then, yes? Is this too simple?
Not for me.
I don't know, because it just dawned upon me that all of you might not know what a vector is, okay?
It's so easy, make it harder.
What is that?
It's so easy, make it harder.
Okay, so, but what do you notice about U1 transpose dot U1? U1 transpose dot U1, I just make this lie on the side, 1, 0, 0, and then 1, 0, 0. What do I get if I multiply using this rule of vector multiplication of dot product between two vectors? I multiply this with that, I multiply this with that, I get, sum them up, I get 1, right? I get 1. Okay? So this is the rule for dot product between two vectors. Okay? And you can generalize this to dot product that involves a dagger. A dagger is just defined to be a vector lying on the side, but you take its complex conjugation also. Okay, you take a complex conjugation. So for this case, it's real. You get this number back. But if you have in vector v1 that is something like j, 0, 0, v1 dagger, which is v1 transpose with a conjugation. Sorry, this is v1 transpose. Okay, v1 transpose is that, and then if you take its conjugation, you get minus j, 0, 0. Okay, and then if you take v1 conjugate transpose dot with v1, will be equal to this number, 0, 0, dotting with j, 0, 0. And what do you get there? You always get 1, okay? You always get 1. That is, if you define this kind of unit vector, it always has the property that its length, its inner product with itself, is always a positive number, okay? That is peculiar about that kind of vector. So, but what you notice about this vector that you have learned about some of these courses, okay, is that U1 conjugate transpose dot U2 is equal to 0. U1 conjugate transpose dot U1 is equal to 1 always. And then you have UI conjugate transpose dot Uj is delta Ij, which is called a Kronecker delta function, which has the value of 1 if I equals j, which has the value of 0 if I is not equal to j. Okay, that is called orthonormality, something like a tongue twister for me. Orthonormality. Okay, orthonormality. Okay. So they are orthonormal. Okay. So given any vector A, and if I expand it in terms of 3 unit vectors, these are called unit vectors. Okay, these are called unit vectors. if I have any vector A expanded in terms of 3 unit vectors, how do I find A1, A2, and A3 easily? Right, I can always multiply this equation by U, say, 2 transpose. Or to be better, I might just want to take conjugate transpose. Conjugate transpose doesn't matter. I want to make a dot product with this. So if I do that on the left-hand side, I will have this. But on the right-hand side, what happened to U2 conjugate transpose dot with U1? Gives me 0, right? The only term that survives is the second term. The third term will also disappear. And what is the inner product, or the dot product? This is called the dot product. Or inner product. Okay, and what is U2 conjugate transpose dot U2? 1. So it gives me A2 immediately. So A2 is just equal to that. So I arrive at the formula that says that AI can be found as to be Ui conjugate transpose dot A. Given any vector A, when expanded in this form, the coefficients can be found easily by this rule. Okay, by this rule. So I can generalize this to n vectors. Vectors of not length 3, but vectors of any length. Okay, I can generalize A to be a vector of A1, A2, AN. This will not be a 3 vector anymore. Usually this is the 3 vectors you use in physics a lot. Okay, this is called an n vector. And drawing upon the same concept, I can have A1, 1, 0, 0, blah, 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 plus A2, 0, 1, 0, plus A3, 0, 0, 1, blah, blah, blah. And so this can be written in general as A1 times unit vector 1 plus A2 times unit vector 2 plus A3 times unit vector 3 plus A4 times unit vector 4 plus AN times unit vector n. Okay, so a general n vector can be written as such. And how would I find the coefficient A1, A2, A3, A4? If I know this, if this is known, how would I find? Very good. Okay, I would multiply this, say, with Ui conjugate transpose, and then the dot product. On the left-hand side, I will have Ui conjugate transpose dot A is equal to, but of all the terms that I have on the right-hand side, this orthogonality principle will also hold for n vectors. That this is delta ij. This is orthonormality principle. Okay? So if I apply this orthonormal property, then what do I have on the right-hand side? Which term will survive? Only one term that survives, right? AI, Ui, conjugate transpose dot Ui. The rest of the terms disappear because of orthogonality. Okay? This is equal to 1 always. I have this being equal to AI. So this is a general formula for AI being Ui conjugate transpose dot A. Okay? And now this concept can be extended to vectors of any length. It can also be extended to vectors of infinite length. Okay, that's what a Fourier series says. Okay, let's see how we expand this to a Fourier series and how we use this rule to find the Fourier series coefficient. Okay, we have, as Mr. Fourier say, over 200 years ago that we have this Fourier series expansion, and that if I can find something that is orthogonal to this function, very much like this rule over here, okay, then I'm done. Okay, so it turns out that if I have a function that looks like this with a complex conjugation, and then multiply by this original function, and I multiply and then I integrate, I sum, okay, from 0 to t. If I do this integral, I can always convince you that this integral always evaluates to 0 when n not equals to n. But it evaluates to something else when n equals n. Okay, I can put a period over it too. Okay? Let me convince you that this always integrates to 0. So if I were to perform this integral, it is j n minus m omega naught t dt. And can you see that when n is not equal to m, this is just, what is that? What is that? Okay. Okay, you're correct. Okay? I just want you to see it faster. That this is an oscillatory function when n not equals m. It will just be an oscillatory function. It has a real part, and it has an imaginary part. And what happens if you integrate an oscillatory function over a period? It always evaluates to 0, right? Can you see that this thing equals 0 evaluates to 0 when n not equal to m? Because when n is not equal to m, I will have an integer value between n and m. And if I look at the real part and imaginary part of this, it's just an oscillatory function with the frequency of omega naught. Omega naught is 1 over t. Okay, when you integrate it, it always evaluates to 0. I don't want to do the algebra to prove it. I just want to argue that it's true. Is that okay with you? Okay? But now, what happens if n equals m? This becomes completely non-oscillatory. It becomes a constant. When n equals m, this is 0. It becomes a constant function. And when you integrate this, what happens? It will just give you t. So it gives you 1 when n equals m. So it almost has this property. Okay, it exactly has this property, not almost. Okay, it exactly has that property of orthonormality. Okay, can you see that? So if it has this property, I can use that rule to find f of n. Okay, so if I have this equality, and if I can do some kind of an inner product, like what I did here, but that will be abstract into an integral inner product, something that you will learn later on. That integral is actually another way of doing inner product between two functions. When you perform the integration of two functions multiplied together, it is actually a kind of inner product. Okay, so actually we are now performing this in an abstract form. So what we do then is to multiply that equation by j m omega naught t, and then f of t, and then integrate both sides, 0 to t dt. This is what I get on the left-hand side. Left-hand side equals that. Right-hand side, I would have multiplied the right-hand side by the same function. Okay, I'm just going to bring it inside the summation. I'm not going to do it step by step. I multiply this by this function, bring it into the summation, and do the integration. So I'm going to hop a few steps here. Okay, is that okay? Multiply this by this function, bring this function into the summation and do the integration. So what I have in the summation is just 1 over t, 0 to d dt, e to the minus j m omega naught t, and then with the leftover thing over there, n omega naught t. Okay, this is what I have inside. So the equation becomes that equation over there. And you see that. Multiply that term by that function and integrate. Or you want me to regurgitate and recapitulate this one? Please. Okay, let me do it again. Let me do it slowly then. F of t is equal to f sub n e to the jn omega naught t. I'm going to multiply this equation by e to the minus jm omega naught t. On the left-hand side, I will have this. And on the right-hand side, I'm going to multiply and take it inside the summation. E to the jm omega naught t, e to the jn omega naught t. I will get this equation. Now I'm going to integrate both sides, okay? Integrate both sides from 0 to t and divided by 1 over t. And over here, the only thing that matters with t is this thing over here, and 0 to t, and then multiply by 1 over t. Maybe I can put the 1 over t here. Can you see this few steps? Okay? So, if I recollect terms over here, this exactly goes to that. Okay, can everybody see that now? Okay? Anybody not catching it now? I can recapitulate if you want me to repeat. Alexander, can you
I was
catch?
saying we're good now.
Good, it's good now. Okay, good. So I have this equation, but what do I know this to be? What do I know this to be? I already worked out an identity for this. This is equal to the canonical delta function. Right? So this is equal to delta nm, the canonical delta function. So the right hand side is the summation of nm, f sub n multiplied by the canonical delta function. But the canonical delta function is 1 only when n equals m is 0 otherwise. What happens to the summation on the right hand side? It just becomes one term. Okay, it just becomes one term, and then the summation drops out. Summation drops out. I only have one term on the right hand side. Finally, I have this equality. E to the j m omega naught t f of t dt must be equal to the right hand side, but only one term survives on the right hand side. Which is the term that survives? If this is canonical delta function multiplied by this and then a sum over that, let me do it slowly perhaps. So the right hand side will just become n equals to minus infinity to infinity f sub n times delta nm. Okay, because this thing is delta nm. When I do this summation, what does it become? Not 1, f sub m. Okay, this just becomes f sub m. Because only that term survives. Okay? So I have a rule for finding the coefficient. This is a rule. And n is a dummy variable. I can call it n again. Okay? So can you see this rule? And this rule is exactly the same as the rules that we have for finding components of a vector in n-dimensional space, but we have generalized it to infinite dimensional space. The same kind of thinking. Okay? Is this clear? Any questions? So this is wonderful. Yes, Alex?
So it looks like the general way we're going to go from converting functions to like finding the Fourier coefficients is we multiply by e to the negative jm omega naught t.
Right.
And then we take the integral from 0 to t and then we multiply by 1 over t. And that's how we
That's
get
right.
our specific
That's right.
coefficient.
That's right.
And we have to do that for each coefficient that we want.
Right. All the coefficients that you
Oh,
want,
leave it in
you find by
terms of
this
that.
method. So this would be m is equal to minus infinity to infinity. Or m goes from minus infinity to plus infinity. You do it for all m's. Okay? But you will find that when you sum this series, you don't have to sum it over all the terms. Maybe only a few important terms are needed.
Yeah.
And you only find the coefficient for the important terms. Okay? So the key to Fourier series expansion is that this is a periodic function. This is also a periodic function. But this is a periodic function with different frequencies, different oscillations. The larger n is, the more oscillatory it becomes. Okay? A periodic function can always be expanded as a sum of periodic functions or harmonic functions of different frequencies. That's what it says. Okay? And they all share the same period. There's one fundamental period that this periodic function has. What is the largest period that you can think of? The largest period of all these periodic functions on the right. Two pi over omega naught. Very good. Okay. The largest period is 2 pi over omega naught. If omega naught is equal to t. Okay, the largest period is t. Essentially, n omega naught t is equal to 2 pi. Okay. So t